Today, the topic of our discussion is inverse of a square matrix. Before coming to the main topic, we need to know what is singular matrix and non-singular matrix. A square matrix A is said to be singular if determinant of that matrix is equal to 0. Otherwise, it is said to be non-singular. That means for a non-singular matrix, the value of its determinant must be non-zero. Now in arithmetic, there are 4 operations: addition, subtraction, multiplication and division. But in abstract algebra, we say subtraction as the additive inverse and division as the multiplicative inverse. Suppose you have a number 2, and if you multiply this number with its reciprocal, that is 1 by 2, we will get 1. Clear? In case of matrices also, if a matrix A is multiplied by its multiplicative inverse, that is A inverse, we will get identity matrix of the same order. What I mean to say, that if A and B are square matrices, definitely of same order, such that AB is equal to BA, and that is equal to identity matrix of same order, then B is called the inverse of A, and we can write it as B is equal to A inverse. On both, this relation satisfy both ways. That means similarly we can say A is called the inverse of B, or A is equal to B inverse. Now since B, we are writing here B is equal to A inverse, now put the value of B in this relation. What we will get? We will get A inverse is equal to A inverse A, and that is equal to identity matrix. Now we have a very famous, we have a very important theorem which says that A into adjoint of A is equal to adjoint of A into A, and that value will be equal to identity matrix into the determinant value of A. So if we see this result and compare this result with the relation AB is equal to BA is equal to I, then we can find that A, first divide this whole relation by determinant of A. What we will get? A into adjoint of A by determinant of A is equal to adjoint of A by determinant of A into A is equal to I. Clear? This is the result what we can prove, but the proof is not given in your syllabus, so I am not going to prove this result, but we will use this result to find the formula of A inverse. Okay. Now since A into adjoint of A is equal to adjoint of A into A is equal to identity matrix into its determinant value, now divide the whole equation by determinant of A and we will have this result. A adjoint of A by determinant of A is equal to I, and this relation holds both way. So by the definition of inverse, that means A inverse equal to A inverse A is equal to I. If we compare this relation and this relation, what we can see very easily, that in A inverse is nothing but adjoint of A by determinant of A. So to find the value of A inverse, we need to find adjoint of A and divided by determinant of A. And from this relation, we can easily say that a matrix is invertible, or we can say that a matrix has inverse if its determinant value is non-zero. Clear? If it is non-zero, then only the inverse of that matrix will exist. And definitely the matrix must be a square matrix, otherwise we cannot find the determinant value. So this is our formula. A inverse is equal to adjoint of A by divided by determinant of A. First, I am giving one example of a 2 by 2 square matrix to find the A inverse. Suppose this is a given matrix. A is equal to 1, 3, 2, minus 1. So first we need to check whether inverse exists or not. For that, we need to know the value of determinant value of A. So find determinant of A. So write its determinant of 1, 3, 2, minus 1, and that value is minus 7. So definitely determinant of A is not equal to 0. So we can say that the matrix A is invertible. Now we need to find the adjoint of the matrix A. For that, we have to find all the cofactors of all the elements. Since this matrix is a 2 by 2 matrix, so it has 4 elements. So we need to find the 4 cofactors. First, the cofactor of A11, that is 1, is minus 1 to the power 1 plus 1, and it's minus 1, 1 plus 1 is define its location, that is the number of row and number of column. So 1 plus 1, so this is positive, and the minor of 1 is minus 1, so it will be minus of 1. Similarly, the cofactor of 3 will be 2, but if we put the sign, so it will be minus 1 to the power 1 plus 2, because its position is 1 to A12. This element is A12. So 1 plus 2, this is odd. So it will be negative of 2. Similarly, the cofactor of 2 will be minus 1 to the power 2 plus 1, because its position is A21. So 2 plus 1, and cofactor of 2 is 3. So it will be, since it is odd, so it will be negative of 3. Similarly, the cofactor of minus 1 will be minus 1 to the power 2 plus 2, because its position is A22. So it will be 2 plus 2, since it is even, so it will be positive, and cofactor of minus 1 is 1, so it is positive 1. So the cofactor matrix is minus 1, minus 2, minus 3, 1. Now, what will be the adjoint of that matrix? Adjoint of A is the transpose of the cofactor matrix. That what we have already discussed. What is the transpose of a matrix? If we interchange the rows into columns, and then it gives the transpose of that matrix. That means we are writing the row minus 1, minus 2 as column. So it is minus 1, minus 2, and the second row minus 3, 1, we are writing as second column, that is minus 3, 1. So it is the adjoint of the cofactor matrix, this. Now what is A inverse? We have the formula adjoint of A divided by determinant of A. So this is your adjoint of a matrix, and divide this matrix by its determinant value, which came out as minus 7, and divide this, if by scalar multiplication, we can say that we are multiplying a matrix by the scalar quantity minus 1 by 7. So each number will get multiplied by minus 1 by 7. So it will be positive 1 by 7. It will be again positive, sorry, it will be positive here. Okay, just make it correct. So it will be positive 3 by 7. Again, this will be positive 2 by 7 and it will be negative 1 by 7. So in the above matrix, we can also verify that A inverse is equal to identity matrix. But I told you in the first relation that if we multiply a matrix A by its inverse, we will get identity matrix. We are going to verify this relation, whether your matrix came out correct or not. So this is A inverse. A inverse into A, that means this is the value of A inverse and that is your A. Now multiply A inverse with the matrix A. Take this determinant value minus 1 by 7 outside and you multiply the by rows into by column formula. The first multiply the first row with first column, then first row with second column. It will give the first row of your resultant matrix, then second row with first column and second row with second column. It will give the second row of the resultant matrix. That it comes out as minus 1 by 7 minus 7 0 0 minus 7 and definitely its value is 1001 and that is the identity matrix of order 2. So clear? So we have already we have our next example. We are taking an example of 3 by 3 square matrix and we are going to find the adjoint and inverse of this matrix. Suppose A is a given matrix whose elements like this: cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. Now we need to find the adjoint of this matrix A first. For this, find the value of its determinant. Determinant of A will be cos theta and then uh, cos theta into 1 minus 0 into 0, that is only cos theta, and then in second term it is negative sign but it has already minus of sine theta, so it will be positive. Then so just ignore the corresponding column and row and you will get sine theta into 1 minus 0 into 0, that is sine theta. So it will be cos square theta plus sine square theta and it will be equal to 1. Now we need to find the cofactor matrix. That means this is a 3 by 3 square matrix. So we have 9 elements. So we need to find the cofactor of all these 9 elements. So cofactor of cos theta, that is A11, capital A11, and that is your value will be A11. When we are finding A11 cos theta, just uh, ignore that particular row and column and find the determinant value of the remaining submatrix. So when we are finding the cofactor of cos theta, so ignore this particular row and column and we are having this determinant cos theta into 1 minus 0. So its value is cos theta. If we put the proper sign here, so according to its position, it will be minus 1 to the power 1 plus 1. So it will give the cofactor of the first element. Similarly, cofactor of minus sine theta, it is the element in the position of A12. So A capital A12 is equal to minus 1 to the power 1 plus 2, the first row second column, so 1 plus 2 and then ignore the particular row and column of this element we are having sine theta into 1 minus 0 into 0. So its value is minus of sine theta. Similarly, we can find cofactor of 0. Cofactor of 0. So ignore this particular row and particular column. You are having this submatrix sine theta cos theta 0 0. So find the determinant value. Sine theta into 0 is 0, cos theta into 0 is 0. So its cofactor of 0 is again 0. Similarly, we can find the cofactor of sine theta, cos theta, cofactor of 0, then cofactor of 0, 0, 1, and you can find all the cofactors by the same method. So after this, we'll have this cofactor matrix. Now substitute the values according to its position: A11, capital A11, capital A12, capital A13, capital 21, capital 22, capital 23, capital 31, capital 32, capital 33. These are values you are writing according to its position. Then we are having this cofactor matrix. Now to find the adjoint of that matrix, we need to write the transpose of this cofactor matrix. The transpose of this cofactor matrix, that means we are writing the rows into columns. Here the row is cos theta minus sin theta 0. So write it as column cos theta minus sin theta 0. Second row is sin theta cos theta 0. So write this row as column. So sin theta cos theta 0. Again the third row is 0 0 1, and so write it as column 0 0 1. So this is the adjoint of the matrix A. Now we need to find out the inverse of that matrix. To find the inverse of matrix, we have adjoint of A divided by determinant of A. Since the determinant value of A is 1, so it will be same as the adjoint of A. So the inverse of A is this: cos theta sin theta 0 minus sin theta cos theta 0 and 0 0 1. This is the inverse matrix of the given matrix A. Similarly, we can find the inverse of this matrix A. The same method, and there is another part. The second part is you have to find first the inverse of this matrix, and then you have to verify that A inverse into A is equal to identity matrix. So you find the determinant value of this matrix A. The determinant comes out as 21, which is non-zero, so inverse A inverse exists. Clear? Matrix is non-singular, so this matrix has inverse. Now find the cofactor of 1, that is A11, cofactor of 2, that is A12, cofactor of 5, that is A13. Second, the cofactor of 2, that is A21, and that is the same way we can find A22, A23, A31, A32, A33. Now when we have the cofactor matrix, find the adjoint by just interchanging the rows into column. So we are having this adjoint matrix, and that matrix is 2, 3, minus 13, minus 3, 6, 9, 5, minus 3, minus 1. Now to find the A inverse, we need to divide this adjoint matrix by its determinant value, that is 21. Now it will come out as this. The first part is over. This A inverse is this matrix. Now we have to prove whether A inverse A is equal to identity or not. So first write the inverse matrix and then multiply this matrix with another matrix A. Same by multiplication rule. first row with each column. First row with first column, that is 2 by 21 into 1 plus 1 by 7 into 2 plus minus 13 by 21 into minus 1. So it will give the first element. Similar way, the first row with second column will give the second element, and first row with the third column will give the third element of the first row. Now the first row is over. We come to the second row. Second row with each column. First row, second row with first column will give the first element, that is minus 1 by 7 into 1 plus 2 by 7 into 2 plus 3 by 7 into minus 1 will give the first elements. Similarly, second row with second column will give the second element. Second row with third column will give the third element. Now the second row is over. Now come to the third row. Third row with first column will give the first element. Third row with second column will give the second element. Third row with third column will give the third element. And it will give the value like this: 21 by 21, 0 by 21, 0 by 21, and so on. And this is your 1 0 0 0 1 0 and 0 0 1, and that is equal to the identity matrix of order 3. Since A was a matrix, square matrix of order 3, so multiplying A by with A inverse, we are getting the identity matrix of same order. Now there is one very important questions of your exercise. It is given in your page number 99. This question number 9.1. There is A is equal to, it is given that A is equal to a square matrix A, B, C minus A. Then you have to show that A inverse is equal to negative of A by determinant of A. So we need to find the cofactor matrix of this given matrix A. So we are having 4 cofactors. The cofactor of A will be negative of A. The cofactor of B will be negative of minus C. Negative sign due to its position. It is 1, 2, 1 plus 2 odd, so it will be negative. Similarly, the cofactor of C is minus B. Minus B due to its position is 2, 1 odd, so it will be negative of B. And then the cofactor of minus A will be A. So cofactor matrix is this. So adjoint is the transpose of this cofactor matrix, and this comes out as minus A minus B minus C A. So A inverse is equal to, we know that A inverse is equal to adjoint of A by determinant of A. So write the adjoint matrix and divide this matrix by determinant of A. So if we take negative sign common as outside, then we are having this matrix A, B, C minus A, and this matrix is nothing but the given matrix A itself. So it will be negative of A by determinant of A. Here we no need to find the value of its determinant, because we have to show that this A inverse is minus A by all determinant of A. So no need to find the value of determinant. Right, determinant of A only. I hope this inverse matrix is clear to all of you. Thank you. Have a nice time.